Welcome, everybody. We are at the 988th monthly meeting, and we have a speaker today, Dan Davis. So to go to the next presentation. Yeah, there it is. So this is our usual agenda: President's welcome, Secretary's report, Treasurer's report, membership report, and there are a couple of people who are new here, so I'm reading it out. Clubhouse report and so forth. Now,
Can we turn the lights down just a little?
well, that's a good point. Lighting, I can do it here.
bit?
All right. Thank you.
Nice. Enough.
Good enough. Okay. So, hope everybody had a great summer. And so I'm going to share a couple of stories I had. The summer, I had a great summer. I went to East Africa and also to South Africa. And while I was there, one of my interests was to visit Bottle Zero Skies. And but a few months back, I went to Death Valley, and it was like Bottle 3, 4, more likely, with all the Las Vegas and the other lights that is actually there. So this was really amazing. So I got to take an iPhone picture, which is only 3-second picture of the Milky Way. You can actually see the shadow of yours on the ground from the Milky Way stars. It was that dark. And this was just the iPhone picture. So I did not do much with it. I just changed some, I just stretched some colors, that's about it. And it was quite an amazing, I don't think the colors are showing up right here. I don't know why.
It's a projector.
Yeah, the projector is. So that was one story I wanted to share, that I know how the skies will look when it is really, really dark.
Are those stars?
Yeah, they're stars, yeah. Some of them got washed out because when I stretched something, it's got washed out, but there are more stars than that, what you see there. But you can really see your shadow on the ground. That really blew me off. I was staying in a lodge there, and so the driver took me off in there, one of those Land Cruisers into the middle of the desert to take some of the pictures. Anyway, I have a couple of points also to discuss from the point of view. But we have a meeting with the MIT group on the 29th to discuss a few things about cooperative outreach activities and also some cooperation in the visible spectrum. So they wanted to meet with us, and definitely last but not the least is the lease renewal, which is to happen next year. So they're going to have a meeting there on the 29th. The other point I want to we'll have a board meeting on the 24th, 8 p.m. I'll send a note out, and members are welcome to listen in. The board members can speak. Another point I want to mention is that we don't have any speakers still filled for January and March, so forth. So if you have any recommendations, if you know speakers who would like to join, then I would like to. So these are mostly researchers and professors and so forth that we would like to. So yeah, that is one open area that we'd like to consider. Yeah, and one last but not the least is that everybody knows about our social media activities, and we do publish our activities in there, and Facebook, Instagram, and so forth, right? And we also have a discuss group where we share. There are about 30-40 people active on it now. So that's another way of also connecting with the group.
So, welcome back after a nice long summer. Just a reminder, like Glenn and I are up here every month, right? It's just to remind you of things that you may want to go out and look at during the course of the month. You probably already know all about all of these things, but our task is to just remind you that these things are available all the time. So without further ado, let's press on. Who's going to work the button? Ben, work the button for me. I like to stand way over here. So you got, if you give me the clicker, I can do it.
Yeah, you want to click?
Yeah, give me the clicker. I can do it. So as mentioned a moment ago, we've had a summer filled with opportunities to observe Saturn's large moon Titan cast its shadow onto Saturn's cloud tops. And remarkably, we had a lot of clear skies. And I observed, which one is is there a pointer on here?
On the left or right?
Oh, yeah. maybe, oh, no.
Already killed it.
Here, you were. Probably should shut down the entire, okay, so we've had plenty of clear skies for the last 4 of them. There's one more coming up on September 20th. They're all happening pretty early in the morning. Titan orbits Saturn every about 2 hours short of 16 days. So 2 weeks and 2 days, all through the summer, we had nice opportunities to see these things. If you've missed any of those and you wind up sleeping through this one, you only have to wait until November of 2038. These shadow transits happen in a series when Saturn's rings appear nearly edge on to us on Earth, and so that happens every 15 years, almost, twice every Saturnian year. And so Saturn right now is experiencing an equinox, and that's why we're seeing the rings nearly edge on, and that's why we're seeing these events. The one on September 20th is up here. This is a Sky Safari show shot, Sky Safari Pro picture of it, and you can. I know John Boudreau is chomping at the bit for this one because he's going to image Titan right next to the shadow, because this one occurs only about a day before Saturn reaches opposition. Yeah. So the shadow is almost directly behind the moon itself, which is kind of cool. Anyway, Ben, the next slide, please. So I thought you said your wife fixed it.
Sorry, this is everything wrong.
All right, so here are two images from Mario Mono. One was on August 3rd, the other one was on September 4th. And I like to pair these pictures because you get to see what's been happening. In the earlier transits, the shadow of Titan crossed the disk closer to Saturn's equator than it did in September. And the next one is going to pass like way up here, which would be a real challenge, I think, for visual observers. The shadow is elusive. It's no more than 0.6 of an arc second across. It's small. It's not like I posted something that I long for. I long for the Jupiter shadow transits because they're so easy to observe as compared to this. But since we have to wait another 15 years to see them, I think you should get out and check it out. We have some more slides, and I'm just going to blast through them just to save some time. But Justin Lutz, that's a nice little shot right there. Sal did that. Doug Paul did that shot. And from what I just said, you can tell which transit you actually are looking at. These are some shots by John Boudreau using his 14.5-inch Dahl Kirkman cast. Those are amazing, amazing images. Trust me, it doesn't look that way visually, but again, you should definitely get out there and give it a shot. So thanks everybody for submitting those images. Also, we had a supernova this summer in NGC 7331. I don't know if anybody had an opportunity to go out and look at that. The challenge of this supernova was that it was very close to the galaxy's nucleus. And so we had the 25-inch up at the clubhouse operating on this on a couple of nights. When it was about 11th, 12th magnitude, it was pretty easy to see in the 25. But I'll bet on a smaller telescope, that'd be pretty hard to see. And Doug Paul sent us this image, and there's the supernova right there, right there. This is a fairly challenging galaxy, all things considered. I've always thought this was a pretty difficult galaxy to observe. It's in a sort of an open area of Pegasus, a little challenging to find it, and it's not particularly bright. I think it's about 45 million light years away. So you get a few 100 billion stars, they're pretty bright, right? But when you put 47 million light years in between you and those stars, things get a little faint. And a nice sketch by Slot. All right, that supernova is currently around 14th magnitude. It's getting really tough to look at. But here's the planet roundup. Venus, as always, tried for daytime telescopic observations. It's 30 degrees away from the sun right now. Currently magnitude minus 3.9 with a tiny apparent diameter, 12 arc seconds. You know, Venus is actually rounding around the back of the sun now. That's relative to Earth. Superior conjunction will occur on January 6th, which will not be visible because it'll be so close to the sun that you can't possibly go in there and look at that. Jupiter is currently at -2 with an apparent diameter of 35 degrees. It's rising about 1:30 in the morning. And Eastern Daylight Time with opposition on January 10th in Gemini. Be very, very high in the winter sky. Really high up. So we're looking through a little bit of air. Maybe if the seeing conditions are great, we'll get some good views of Jupiter this winter. Next slide, please. Uranus at magnitude 5.7, actually pretty easy to find this fall. If you can find the Pleiades, I'll bet you can find Uranus. It's 2.6 degrees southwest of 37 Tauri. Opposition's coming up in November. Pleiades, easy start to seeing your finest stuff. This is a 5-degree finder ring. And there's Uranus right there. A little fainter than 37 Tau, but in the eyepiece, in the finest scope field of view, it's actually a pretty easy thing to pick up. And Uranus is fun to look at. It's a grayish blue disk, and if you really warp up the magnification, you might, at near opposition, you might see some of the moons of the planet. Next slide, please. Neptune, equally easy to find this year because it's in the same low power finder field as Saturn. It's only 2.4 arc seconds in diameter. Opposition's coming up in about a week and a half. If you come up to the clubhouse, Eileen has asked me to run the 25-inch during the picnic. If you come to the picnic and it's clear, ask me to find Neptune, and we'll look at Triton, the big moon of the planet. It's a magnitude 13.6. It's 15 arc seconds from Neptune, which is actually pretty close, but we can certainly see it in the 25-inch, and I would invite you to come over and take a look at that. Next slide. And finally, I saved the best for last, of course. Saturn is reaching opposition also on the 23rd of September at a distance of only 795 million miles. The rings are tilted right now at 2.2 degrees. It's transiting the meridian at about 1:30 in the morning. By mid-November, the ring tilt will be 0.4 degrees. That's what it will look like, if you can even see the rings. 0.4 degrees. That's about as edge on as they're going to get for us. And so that'll be a fun thing to actually watch. Next slide. Glenn, you're still here, right?
I'm still here.
I haven't put you to sleep yet? Okay.
Nope, not yet.
You know, I've started to include lunar highlights, and I've been pointing out some of the easier features to see on the moon, and I would encourage you all to grab a telescope, go out and look at the moon. While your imaging rig's over there doing its imaging thing, just grab a small scope and look at the moon. I was out last night, this morning, at about 1 o'clock this morning, checking out the moon. It was awesome. It was so awesome. And so was Saturn too, but here are 3 craters. I can hardly contain myself. The 3 craters, Ptolemaeus, Alphonsus, and Arzakel, are 3 really prominent craters. I like to look at Ptolemaeus when the sun's low in the lunar sky. When the sun rises up a little bit, that flat floor of Ptolemaeus looks very flat. But if you can catch it when the sun angle is low, you can see all of these ghost craters that cover the floor of that crater, buried by lava, buried by magma. So it's a fun crater to look at. Alphonsus, under a little bit of high illumination, shows dark volcanic vents along the walls of the craters. And well, it's the fun part of the moon to explore. So I would encourage you to go out and check that out. All right, next slide, please. The fun double star of the month. Glenn, why don't you chime in about, you're the double star guy. Why don't you tell us about Gamma Delta?
Okay, I'm just looking here. I've lost the pictures here, but so I'm going blind. I don't know. I just lost the screen and everything. Anyway, so the slide is up for the double star?
Yeah.
Yeah, I don't know what happened. Let me just try something here.
No, just tell us about
I'm gonna have to talk. I'm going blind, unfortunately. I'll see if I can get back on. I'll talk about the double star. I can't see anything at this particular point. Anyway, Gamma Delphini is the double star of the month. And I'm just getting myself back on the program here. It's a beautiful pair of stars. There we go. I'm back. Okay. Well, I get Zoom workplace here. I'll get some slides jumping at me here. Leave meeting. I don't want to leave the meeting. Okay. I don't know what's happening at my end.
You work your
I can see the screen now.
So these two stars
are anyway.
All right, I'll be quiet.
Can you hear me?
Yes.
Okay, I'm back. Yeah, I've got a little glitch here. I'm getting some notifications that my internet connection isn't that good. So if I blank out, it's all yours, Rich. Yeah, Gamma Delphini is one of the prettiest double stars in the sky. And it's in the constellation Delphinus. Obviously, it's the nose of the dolphin itself. And Rich has got everything down there. It's fairly similar in brightness, but there are different spectral classes. It's a K-type star with an F7 type star. And I've seen a color contrast. Most people describe this as kind of a yellow-blue type of combination. I saw it as kind of a pale yellow and a pale blue. What's key, though, is it just maybe about 15 arc minutes, a little bit south of that, there's another double star, and it's a beauty. It's Struve 2727. Magnitudes are 7.5 and 8.2. It's just 6 arc seconds separation, and it's a pretty little double star. And sometimes when I evaluate double stars, and this is with small telescopes, I consider the ones like Gamma to be like a first tier double star or binary, where both components are, the star itself would be naked eye, and both components are at least brighter than 6th magnitude. This one I'd say is a classic example of a second tier type double star. They're fainter, they still show well in the small telescope, and to me, the third tier double stars are the ones that are down around 9th and 10th magnitude, and those are very faint. But it's a beautiful sight, and like if you got about a 60 power view, you'll see both double stars, and it really is kind of a striking sight. So when you're looking at Gamma, look for that little double star as well. Great sight. Next.
And while you're in the area, M15, M71, and a few nice NGC objects are there for the offering. There are a couple of convenient minima of algal coming up. Algal has a magnitude range from 2.1 to 3.4 over a 2.87 day period. Monday, September 22nd, at about 11 o'clock in the evening, algal will reach a minimum brightness. And again, there are others around this every 3 days, but conveniently placed ones, time-wise, are Wednesday, October 15th at about 9:30 p.m. I always, whenever I go out and I look at the sky, I always immediately look to see if algal is upright or is it about the same brightness as Rho. At minimum, these guys are about the same magnitude. So you can get a quick feel for where algal is in its cycle if you just compare it to Rho Persei. So it's an eclipsing variable star. You all know about that. And so just check it out whenever you get a chance. All right, next slide. There's a comet in the sky that might prove to be interesting come October. It's Comet Lemon, C2025A6. Dano? Yeah? Your wife?
She's not here, right?
I'll call her. You can see the path of this comet, it's right up here, right now, in Lynx. And it's gonna traverse underneath the Dipper and down into it's the morning sky object. But there's some hope that by mid-October, it'll be about magnitude 4.5. Oh. And it's got some nice green color to it already. The green color is from diatomic carbon, which is a rather exotic molecule itself. I would challenge you to draw a Lewis dot structure for C2. Pretty hard to do. Anyway, so more about that at the October meeting. All right, next slide. What else is next? Oh, there's some satellites coming up. I know you all love satellites. I was up in Maine with Bruce in the back for a week, nice dark skies. You couldn't look through the eyepiece of my telescope for more than a minute without a satellite streaking through the field of view. They are everywhere. And I don't know if you guys look at the Sky and Telescope website, but there's a scary article about, I can't remember the name of the satellite. They're proposing that they're just gonna project beams of sunlight down to cities.
That's horrible. Yeah. You're gonna get 2% more illumination for 20 minutes for solar panels.
So let's hope that whole thing gets nixed.
Please.
But while you're out looking at other stuff, the space station is gonna make a pass on Saturday night, at about 10 minutes past 8, across through get my bearings here, across the northwestern skies. A few minutes later, Tiangong, the Chinese space station, also makes a path. And you know, you've heard me say this before, when I talk about observing satellites, especially the International Space Station, I always give a homework assignment that if you've never looked at the space station through a telescope, you owe it to yourself to do so. About 30 power, if you're using a telescope with an aperture of more than 6 inches, I recommend a moon filter to cut the glare down. But with 30 power and a telescope, now remember, you got to track it across the sky, so it should be a mount that's convenient towards that. But you can actually see the solar panels, you can see the modules of the space station. It's pretty cool. It's as big as a football field in every direction, and it's only about 240 miles high. So that's your homework assignment. If you've never looked at the space station, through a telescope. You should really do it. It's pretty cool. Anyway, next slide, please. The July challenge was NGC 6181. Glenn, you want to talk about this?
Okay, I'm glad I got the picture back, but it was a little scary. Just a quick personal notice. My wife this couple of months ago was diagnosed with an aggressive form of lymphoma. So that's why I wasn't at the last couple of meetings, and I'll probably be missing a couple coming up, but she's doing well. We're fighting this together. So I miss you guys. I'm looking forward to being back there in person, fairly new. As far as the July challenge, it's NGC 6181. It's a spiral galaxy in Hercules, a little bit south of Beta Hercules. It's about 12th magnitude, and it's about 2.5 arc minutes by 1 arc minute. That's if you're photographing it. And you see Mario's picture right there. We'll go to the next slide, and then we'll look at the ones that some of our members took. Justin Lutz and Dave Giordano. If either of you is there, if you want to explain the notes on your particular image. Okay, if there's no response, we'll go to the next. We'll just show the slides.
Yeah, hi. Sorry, Justin is here. Can you hear me?
Okay.
Yep.
Yeah, so this was taken with my C11 with a 0.7 reducer in my backyard on my EQ6R Pro. I forget the number of exposures. It was a couple months ago now, but probably I usually do like 10 to 15 hours total exposure. I usually do like 3-minute subs and processed in PixInsight.
Okay,
Thanks,
Dave.
Justin, you're right? I don't think Dave's here. All right, how about if you go to the next slide?
All right, it is me. That's a C star image, by the way.
That's a C star image.
That's a C star, that's 52 hours exposure, but I did stack it in PixInsight. Yeah.
Does it do live stacking?
Yes.
Yeah.
And I also saved the, for 20-second.
One of our members, Mike Drewer, was up in Maine with us, and he was using a C star to image some galaxies, and it came out amazing,
Yeah.
just amazing. He was doing live stacking
Yeah.
on his. And Doug, you want to comment on yours?
Yeah, that's about 3 hours with a 6-inch aperture.
Okay. Pretty cool. All right, next slide, please. This is Glenn's, no, this is Vlad's, Slav's sketch, which I did the very best I could to make it look reasonable on the screen. But that's with this 22-inch job. So probably, I don't know where I was observing from, but not bad. Oh, from Worcester. From Worcester. All right, next slide, please. So the August challenge was Webb's Wreath. It's an asterism in Hercules. And that's, we saw this slide last month, or in July. That's Doug Paul's image with the wreath highlighted there. And if you want to find it in Hercules, it's, it's a Cerebus the dog here. I think that's Cerebus the dog. 100 Hercule and 89 Hercule, and the wreath is in there. It's a relatively small asterism. I've not seen it. I honestly haven't gone out to look for it. But it's an interesting little asterism. So we've got a couple more slides of it. If you want to hit
Yeah,
the
I can
next
jump
slide, please.
back in before you do. I'll jump back in on that one. It's a small asteroid. It was discovered again by Webb, T.W. Webb. He was the author of Celestial Objects for Small Telescopes. And what I liked about this, if you look in that picture there, the wreath itself is actually below that star. There's a star right in the middle. Below it, there's about a handful of stars and like a semicircle. That's the actual wreath that he saw. Others have been added. And if you follow that arc a little bit more, it almost looks like a chambered nautilus, the spiral of a chambered nautilus. It continues around that star. So there are some added, but the actual wreath itself is probably 5 arc minutes across. And I did look at it with a 10-inch telescope, but it could be viewed with telescopes smaller than that. We'll go to the next slides now, and I'll let Rich pick up as far as getting comments from people.
Can you see it? It's right here. Right here. Right there. Michael, you here with us tonight?
Yeah, I'm here.
I don't hear.
Mike,
Okay.
Mike, what
Can
you
you hear
shoot this?
So this is that Dwarf 3 that I got courtesy of Stellophane's raffle, and I entered the coordinates for the web for this in there, set it out in the backyard, and I'll be darned didn't find it and take an image of it. Trying to remember, this image wasn't,
To the computer.
I'm not sure, I forget how long this image was stacked. It wasn't one of the longer images that I did. But I barely claim any credit other than just actually setting the silly thing out there. I was shocked at how well it did. Over.
Nice, thank you. All
And
right,
I
next
would
slide.
want to notice if you look at the upper left-hand corner, that bright star, that's a double star, 100 Hercules, which is a beautiful, we'll go back a slide there. Yeah, that star at the upper corner, that's 100 Hercules. It's a beautiful, they're both about 6 magnitude 14 arcseconds. So there's a showcase double star. Now we'll go to the next slides.
So Dave Martin, Dave Giordano. Are you guys here tonight? All right, how about the next slide? This is Mario's slide. Oh, David Hines with the Unistellar. It recorded almost so many stars, it's hard to see the read. How about the next slide, please? And this is Mario's that also showcases some really, really far away galaxies. That may be a little hard to see on the screen, but
Yeah, I don't know if this is the deep shot. Oh, yeah, no, this one's labeled with
I can't
galaxies.
remember.
This is weird. I mean, Roger first asked me to get it because he needed it for an object, and out of the blue, Steve O'Meara gives me a call and says he needs a picture for Sky and Tel with the galaxies. I said, you've got 3-inch refractors in Africa, and you want to take pictures of people who look for galaxies that are 14 and 15 mag. So I took that for him. That they used a negative in Sky and Tel, but you really need a large scope to see these galaxies.
Oh, and very dark skies. All right, next slide, please. And this is Glenn's sketch, right? Yeah, Glenn Chapel's sketch. Nice job.
Just
Glenn.
shows
Those are the
again-
10-inch.
This is with a 10-inch, and I made a note of where 100 Hercules is. It was just outside the field of view, but again, it showed very nicely with that particular telescope. And we'll go to the next slide.
Here's the September challenge, NGC 6540 in Sagittarius. Time is running out on this one. I know it's the September challenge, but by the time it gets dark, Sagittarius is already sort of slipping into the southwestern skies. And it's, catch this one if you can, catch it early. It's a, Mario, that's Doug Paul's image. I mean, the star field is so rich. I've looked at this with my 20-inch scope once decades ago, and I could see it as a faint smudge of light, but it seems lost in the star fields here. In some of the
When I
pictures.
took it, it's just a field of stars.
Yeah,
Yeah, it's just that little thing in the center.
yeah,
I looked at the Wikipedia article and it's so full of other stars that you can hardly tell what the object is.
yeah, yep. All right, next slide.
Yeah, it's about 4 degrees. It's about 4 degrees from the galactic pole.
Oh, the galactic center.
Clear.
You mean the galactic center, Glenn, right?
Or
Let's see what I have here. Yeah, the galactic center. My apologies.
So the October
And the
challenge.
one,
Go ahead.
no, go ahead. You can finish it up, Rich. I'm just going to tell everybody keep looking up. And again, I hope I'm back in person in the near future. Thank you.
See
Go
you
ahead.
next
You can
time.
finish it.
Okay, so how many people have never seen the Helix Nebula? Anybody who all seen it? Good, okay. This is a challenge object. It's large, faint, and it is best seen with a wide field. It's about half the size of the full moon. Best seen with a low power wide field. Here's the challenge for you. See if you can see it in your finder scope. Hold an Oxy 3 filter or UHC filter over the eyepiece of your finder scope and see if you can see it in the finder. If your finder scope has an eyepiece where you can insert a filter, pop a UHC filter and see if you can spot it. And then if you're in a really dark sky, hold that filter up to your eye and see if you can actually see it with your eye. It's fairly large in the sky. You might be able to actually see it if you've got a filter up against your eye. It's a great object to look at, and I can't wait to see what the images do with that one. It's in a kind of open area. I've always found this a bit difficult to find. This is Fomalhaut, and they're the eastern stars of Capricornus, so it's sort of in between there. If you can get to, I think that's New Aquarii. You can find it, but it's a tricky object to find, but it's nice and big, you should be able to see it. It's one of the nearest planetary nebulae to us. So that's a nice October challenge coming up the next month. All right, next slide, please. Could be it. Here's our clubhouse observing schedule, all the way through the rest of the year. Again, if the skies are clear, there'll be a clubhouse member will be up there to open the place up and lock it up. People are taking, their images are there, visual observers are there. It's a lot of fun. Come, enjoy the equipment. Next slide, please.
Let me introduce our speaker for the day, Professor Dan Davis, and the talk title is Tectonics Around the Solar System. Our speaker on tectonics around the solar system is Dr. Dan Davis, retired professor of geophysics at Stony Brook University in New York. Tectonics is a study of the structure of the crust of the planetary body, how it deforms, and the forces driving that movement over geologic time. Dr. Davis will review the tectonics of the solid planets and moons across the solar system and examine the forces and energy sources driving their diverse tectonic styles and how they compare to our own planet Earth. When he got his first small telescope, he discovered that even in a city, he could see the planets and especially the moon, on which he saw his first glimpses of geology. I have to jump 2 slides, by the way. All right. While studying at Princeton University, he worked all 4 years as a research assistant in astrophysics, but he majored in geology and geophysics. He continued the study of geophysics at MIT, where his PhD work focused on the mechanics of mountain belts, and the driving forces of plate tectonics. After postdoctoral fellowship at Columbia, he joined the faculty of Stony Brook, where his research included geophysics of plate convergence. In retirement, he is concentrating mostly on grandparenting, stargazing, and moon-related projects. With his friend Guy Consol-Magno, he's a co-author of Turn Left at Orion. By the way, that's the first book I got as a present 5 years ago, before I jumped into astronomy. So thank you, Dan. It's a guide to the beginning stargazers that is now in its 5th edition and 5th language, 4 of which Dan says he cannot read. All right, Dan, all yours.
All right, I think we're all set up here. So I have to admit to you that what I have in mind for this evening isn't technically an astronomy talk. I'm a long-term stargazer, so I look up. I'm a geoscientist, so I also look down. And in a combination of those 2 perspectives, I want to take you on a little bit of a whirlwind tour around the solid bodies of the solar system, looking for tectonics, which is sort of my field of research specialization. Now, a friend, Guy Consolmagno, and I have had this book out that Bennu mentioned for ages. It's been a huge amount of fun. We come from slightly different perspectives. Guy is a geochemist and very gifted writer and public presenter and so on. I'm a geophysicist, and of the 2 of us, I'm more the stargazer. He just, he's much more serious. I'm a much more serious stargazer than he is. Well, I was the one who was proposing objects for the book and doing the drawings and so on. I told him about this triple star, which Beta Monostratus, which actually was the triple star of the month in April. And this was way back when, and he said, Beta what? Because it's not a very prominent constellation, Beta. And he took enough Latin to know, it was the unicorn. He said, where is that? And I said, well, in winter sky, you look towards Orion and you turn left. And we kind of looked at each other and said, oh, that'd be a cool book title. It was meant to be nothing more than a friendly introduction and a way of demystifying things. But at least one person appears to have taken us a little bit too seriously. I couldn't believe when I found this picture. So as a kid, the proceeds of the paper route went to my getting my first real telescope. Anybody remember what this is? Unitron, which
2.4 inch.
2.4 inch Unitron 114, and it or one of its sisters would grace the back cover of Sky and Telescope every month for years. And I just drooled after this and I wanted it. And finally I got this thing and I still have it. I still have it. And I have a number of other telescopes to go with it. So it's been said that the first step in admitting you, in first step of dealing with a project and a problem is to admit you have one. Hello, my name is Dan and I have a telescope problem. So the littlest of those telescopes is the Sea Star, and I recently completed a Messier album with it, which was fun to do. So I'm just going to pull out one of these objects that I think this crowd will immediately identify. Obviously, yeah, I'm 27, and you know it's for a little Sea Star. This is a great image, and you see all this wonderful color and detail. Well, I was recently at Cherry Springs, and with my 14-inch dove, it is a magnificent object, but it doesn't look like that. It's magnificent in a different way. What you see in the telescope isn't what an image, a photograph shows you. Nothing wrong with what you see in a telescope, but they're different. And you have to recognize that difference. And that is true of pretty much anything you look at in the sky. Okay? No matter what, whether you're looking at a small refractor or a 8 or 10-inch dove. That's doubly true in this part of the world. This sad image shows night sky brightness. Okay, it's pretty horrifying, and it gets worse if you zoom in. You are here, and I grew up on the edge of the Bronx, and even back then, it was pretty. I was looking over the Bronx in Manhattan. So, and I had this lovely little 2.4-inch refractor, and like, what can you look at? Well, there is indeed one easy telescopic object that looks exactly like its photographs. And not only that, it shows geology. And that, of course, is the moon. And not only any geology, but you can easily see Rim Aridaeus, which is a graben, paranormal faults extended, making this rill. You can see this amazing escarpment, which is what remains of what was once the multi-ring basin appearance of around Mare Nectaris a long time ago. So I'm going to ask people here, what is this place? Anybody know what it is?
That's Apollo 15 landing.
Apollo 15 landing site, exactly. I figured this is a crowd where people would know that. Apollo 15 had at least 3 special things about it. One was the first one with a moon rover, where they could, therefore they could go bigger distances. Second one was the commander was Dave Scott, who really took the geology seriously. I know well one of the guys who trained him, and the scientists loved Dave Scott. The third, and to my mind, as a kid, best thing about Apollo 15 was that it was during the summer. I wasn't going to school, and I could watch every EVA. And I knew the area really well because I had my Unitron 114, and I could look at it. And thanks to people like Tim Much from Brown, there were diagrams like this that I at first found kind of, what are these funny, Husk, Elm, Heck? But it was possible, even just looking from the Earth, to begin to draw geological maps of the moon. So that was my first introduction to geology. And I knew things like Imbrian and Eratosthenean, Copernican eras long before I went to college. I took my first geology course and learned about Cambrian Ordovician, Silurian, Devonian, and all that stuff. So to me, the Earth was the second planet in which I learned about some geology. Kind of ironic. even without having gone to the moon, it was possible to come up with a stratigraphy of the moon because, well, anything that gets covered by the very widespread ejecta from Mare Nectaris is pre-nectarian by definition. They get covered by the stuff that came out of the impact that hadn't been there before. And the same thing for the Imbrium impact. And depending upon whether have really bright rays still or faint rays, you can also put them into the Eratosthenean or Copernican theories. Well, then you can say, well, things like this is the general time period when the late heavy bombardment happened and most Mare got filled in. It looks like lunar history has been spread out really well through time until you look at what I've done to these dates. The Eratosthenean, which is late, is all the way back there in time. So lunar history is very much compressed towards the beginning of the history of the moon. But the thing to remember about it is that geology is the study of what happens during all that time. My field, tectonics, is what goes bump in the crust during that time. Okay? It's basins excavated, collapses, mountains forming, thrust faults, graben, and so on. And that's the kind of things I want to look at through the solar system with you. Now, what can tectonics do to the crust? This is me with a Pakistani friend at an amazing fold. And one thing that can happen is, geology likes to lay down layers pretty horizontal. You can have folding that folds it and shortens it. Or the other way to shorten it is a thrust fold, like this one a student is looking at in upstate New York. And the key thing about a thrust fold is this. If you've got a dipping fault, for reasons going back to old time miners, the surface you'd hang your lantern on was called the hanging wall, and the one you'd stand on is the foot wall. If the hanging wall goes up, you notice my elbows get closer? That's called a reverse or a thrust fold. And you can see that they are associated with crustal shortening. The only person handy to model this for me, who I disturbed from her quilting studio, my wife, is demonstrating how a thrust fold works here. But alternatively, she can have the hanging wall go down, in which case the elbows move apart. In other words, you have extension by normal folding. Okay, you're going to be hearing these words thrust and normal folding, so it's important to keep in mind the difference, contraction or extension. And the third thing that can happen is side to side. This is in Orange Grove in Southern California, and you could see that either the person laying out the trees had a really, really overactive Saturday night, or that after they were laid out, there was a strike slip earthquake. On Earth, we've got tectonics on a really, really big scale. This is a field area that I went to in the past, will not be going back to, and haven't gone to for a while. Those tents are part of an Afghan refugee camp. This is in Western Pakistan on the border of Afghanistan. But the important thing about this is that there's something wrong here. Older stuff is supposed to be below younger stuff, because that's how they get laid down. Here, you have older Paleocene limestones over younger Eocene shells. Well, how'd that happen? Thrust folding. And thrust folding is associated with contraction. Contraction is what happens at plate collisions, like the India-Asia collision, which is forming the whole Himalayan system. Now, to stay on this planet of ours for a minute, there's an important term here I gotta mention. It's lithosphere. And the quick way to describe lithosphere is it's the outer shell of a planet that behaves the way you think a way you think rock should behave. It consists of that chemical scum on top that we call crust, okay? Which is really the result of mixing and melting and processes with metal material, and the lighter stuff winds up one way or another on the top. So it really is, we are scum living on scum. Plus, whatever part of the upper mantle is rigid, right beneath it. And on Earth, we have new crust created at mid-ocean ridges, hot stuff comes up, and conserving surface area on the surface of the Earth, you've got cold stuff going down in subduction zones. The reason I mention it is why this is all about heat transfer. Plate tectonics on Earth is a driving part of how the Earth gets heat out. And that's how we're going to compare a lot of objects around the solar system. This is a plot of heat flow in the Earth. These units are milliwatts per square meter. You make a square meter and just ask what's the rate of energy coming out in milliwatts. And there's many ways to measure this. Some of them are quite hilarious. I was involved in one that was basically sending a 30-something foot dart down 4 kilometers to the ocean floor with thermal sensors. You don't want to get in the way of that. But over time, these data have been collected, and you can see that the place where heat is really coming out is definitely controlled by plate tectonics. It's spreading centers. So no matter what planet or moon you're looking at, the active tectonics, which is what I'm going to be interested in, comes down to where does the heat come from, and then how is it released? Okay, those are the key things we're going to be looking at here in comparing objects. Well, this heat engine we call the Earth runs on the equivalent of about 40,000 nuclear power plants. Okay, if you have 40,000 nuclear power plants, the heat they put out is pretty much the heat that's coming out of the Earth. And in our particular era of geological history, about half, maybe a little over half, but about half is being produced as we speak by the decay of uranium, thorium, potassium. The other half is left over from the beginning, primordial heat. And what do I mean by primordial heat? Well, when you bring in all those planetesimals, all that potential energy, obviously you're producing a lot of heat. When you have a molten Earth and it's beginning to cool, and a lot of the iron decides to bond with iron-loving siderophile elements and sink to the middle to make a core, that's more potential energy released, more heat. And then, of course, the big splat of a Mars-sized object that wound up producing the moon. So there was a lot of heat to start out with. You had the whole Earth really, really hot. So you've got the primordial and ongoing radioactive produced heat. And the question is, how does it get out? Well, there are a number of peculiar things about geologists. One thing is ways in which we should never be trusted. Never trust a geologist who says the words recent or fast. Okay, we have different concepts of those things. And the other thing about geologists is this absurd obsession with triangular shaped diagrams. We call ternary diagrams. And generally we use them to say if there's some mineral assemblage, making of some rock, how much of it is thing A, how much is thing B, and how much is thing C. But you're going to be seeing a lot of this. As I ask, how does the heat escape? You think about how do you get heat out of a planet? How do you get heat from point A to point B? Ever? Well, one way is if you got anything that's hot on one side, cool on the other, you're going to just have that heat move through it. It's going to conduct through, right? And you've got, whatever 20 degrees C average here and 1,000 down there. So obviously, conduction is one way. Another is volcanism. And for the Earth in particular, a special kind of volcanism. If you've got 2/3 of the Earth is mantle, and there's going to be slight fluctuations in time, in conditions, particularly towards the bottom, maybe a little more radioactive elements, or maybe just whatever, and you're going to have an area that's a little bit warmer. That being warmer makes it less viscous, so it'll flow easier. Also makes it less dense, so it wants to go up. So it starts to go up, and this can become a runaway process and produce what's called a mantle plume. We have material coming up, kind of like a Bunsen burner, on which you then take a sheet of plexiglass and move it over. Well, you are, over time, going to be burning different parts of that sheet of plexiglass, right? So about 5 million, whatever, 4 to 5 million years ago, what we now call Kauai was over the hotspot and produced an island there, but then it moved too far away for the plume to get to it. So it started making Oahu, then Molokai, then Maui, and finally now what we call the Big Island of Hawaii. Okay, so that's a second mechanism. Volcanism, specifically hotspot volcanism. And the third one is the one we've already mentioned, plate recycling. Hot stuff comes up at mid-ocean ridges, cool plates subduct. In a ternary diagram, if you have a planet where all the heat comes out by conduction, it would plot here. If it was all hotspot volcanism here, if it was 1/3 of each, it would plot there. The Earth is mostly plate recycling, but a significant amount of conduction. It's not zero hotspot volcanism. If it were, it would fall exactly on somewhere on that line. But this shows that for Earth, the heat gets out, mostly plate recycling, with conduction being fairly important, and a small contribution from hotspot volcanism. But our Earth is only one of the 5 big solid bodies in the inner solar system. So let's take a look at the others in order. Which one is this?
Andy,
What's that?
Andy, Mercury.
Mercury. Right, why do you say Mercury? Because it's got a lot of light colored stuff that looks like the North City crust of the moon. It doesn't have a lot of Mare.
Far side of the moon.
Far side of the moon. Yeah. And I'm going to take you on a little tour. How many people here have ever played? Well, I think most people have played with Google Earth. You've seen, how many people have played with Google Moon? It's cool, isn't it? And you can make movies with it. I'm going to take you on a little movie to a place you've already been. And of course, we're coming back to the Apollo 15 site, which I love. Hadley Rill next to Mare Imbrium. Just think about this place, though. Here's this big Mare. We're going to go into a collapsed lava tube that is 1,200 meters across, 1,000 feet deep. Just contemplate the volume of magma that moves through this thing, and we're up on the edge of a big mountain range. Now we're going to rotate around. I sort of landed us near the Apollo 15 landing site. Just like Google Earth uses images taken from above, like planes or whatever, even some satellite. This Google Moon uses images taken from lunar orbit by various spacecraft, particularly the Japanese one. And it's pretty good resolution. And to give you a sense of how good it is, this is what I got out of Google Moon. I'm now going to slowly transition it into a picture taken by the Apollo 15 astronauts. Oh, not bad, eh? And the degree to which it missed is my fault because I didn't come down to exactly the right spot on the moon. But it's very good. We're looking at Mount Hadley here. That's higher than Pikes Peak. I mean, that is a serious bit of mountain building. And to a geologist, that's, egad, just do the math on the amount of energy taken to raise this up. So clearly it's been tectonics of a form on the moon. We've got to put it into context. We're here in the Apennine Mountains, which is sort of the best surviving bit of this ring of the Mare Imbrium impact. when I showed you that lunar geological history before, the last of the big impacts was Mare Orientale. Now, how many people here have used a favorable libration to actually look at Orientale? It's really cool. You can see that there is a very impressive ring structure to it. Well, that's a look back at what Mare Imbrium was like, and before that, Nectaris. So yes, impressive tectonics, but it's all exogenic. It's not what the moon did to itself. It's the moon being a passive victim of the hit and run, hit and not run, hit and explode. And the result of this huge cavity, causing flexure of the crust and collapse of the sides and making the Apennines and later opportunities for basaltic magnetism. So that's not to say that the moon isn't a geologically interesting place. This is a USGS map that came out just about 5 years ago. And I'm going to concentrate on the eastern equatorial region here. I'm gonna ask you to look at it and take my word for it that there's, this means E's being and I's mean different eras, and then the subscripts mean different things about the type of material that's mapped. I wanted to look at some point on this while I make a transition from this map to an image I took in my backyard with my 4-inch Apo. And the intent of this is to convince you that you can see the geology with a small telescope. Okay? It's there. You can see it. So there is real geology. There has been amazing tectonics, but it's ancient tectonics we're looking at. And most of that tectonics was in response one way or another, directly or indirectly, to impacts. So it's geologically interesting, but not even close to having plate tectonics. What about Mercury that I tried to deceive you into thinking the first object was? Well, I have a special relationship with Mercury by family, if you will, or inheritance. My PhD advisor, Sean Solomon, was the chief scientist on the Mercury Messenger mission. And being his former student, I have, well, my students think they have the right to give me a hard time about things. So I do the same to my former advisor. And you'll see a way in which I teased him about Mercury. The story with Mercury is, you look at the surface, it's highly cratered, so it's old, but it's got a lot of thrust faults. Remember, thrust faults are the ones that mean shortening. Well, if you shorten one place, you got to extend somewhere else, right? Unless you are decreasing the size of the planet itself. And that's what happened with Mercury. Its big core cooled, the planet shrunk, and it had lots of thrust faults. So you have images, doctored a bit here, but images that show thrust faults cutting across craters and even changing the shape of them and so on. So Mercury really, its tectonics is simply from the fact that it shrunk. So what I did to my former advisor in a scientific meeting, at the end of it, I dissed his planet by comparing it to something else that had shortened as a result of shrinking. Remember, there were two ways to shorten, I said. One is thrust folding, the other is folding. So if you want to understand the tectonics of Mercury, look at an old apple, right? It's the same thing, only its crust had to shorten, but because of the rheologies involved and so on, it did it by folding instead of thrust folding. So that kind of puts Mercury in its place, right? Its tectonics is all related to the core having cooled, and it's ancient. That also allows us to put the moon and Mercury on our diagram. They don't do plate tectonics. They don't do hotspot volcanism. Whatever heat's coming out, and it has been measured on the moon with some difficulty by astronauts, is conductive. Mars. Well, even this National Geographic map shows Mars is like wildly geological. Let's go to sort of the most famous place on Mars, Valles Marineris. Now, the emphasis is, for a thing about Mars is follow the water, think about life. And it is true, you can look at Valles Marineris and see all sorts of evidence of it having been shaped by water, but it wasn't created by water. Mars was created by sets of normal faults that cause a drop down area between the normal faults called a graben. German word, the same as the word for grave or ditch. That means that there has to have been extension. It means there have to have been tensional stresses. What could do that? You need something anomalous, something weird and uniquely anomalous on that planet to make that possible. And that place, of course, is Sparsus, this huge bulge that includes these amazingly huge shield volcanoes, the biggest of which, Olympus Mons, just boggles the imagination. The caldera itself is 50 miles across. Got 6-kilometer cliffs. And the output of basaltic magma, and therefore heat, when this formed, when this was active, is just astonishing. It definitely took care of helping to cool that planet down. But it's, on Mars, it's not all volcanism, it's not all that simple. Let's look at another spot on Mars. Cerberus Fossae. Another place, it's been shaped to some of the gullies and things, water related and later filled in with sand dunes. But a geologist, at least one who was trained by me, I hope, would look at this and squeeze this area and say, what the? And want to zoom in. So here we see a surface. What do you notice on that surface? Craters. What does that tell you about that age, that surface? It's old, been there a long time. Sand has tried to cover the craters, but it's been there. Below that, you see some horizontal layers. But then what do you see below that? You see a whole bunch of layers that are tilted down to the right. This sets off bells for any geologist. It's what we call an angular unconformity. So it's where there is a surface where older deformed material is cut off and new stuff is placed on top of it at an angle that doesn't conform. So this box, kind of, you can see how that box, the orientations in this box mimic what's in that corresponding box up there. So what does this tell us? To geologists, unconformities tell a story. You get layers deposited. Okay, then some kind of tectonics causes those layers to tilt. Well, you're in a body that's going to have any kind of erosion, water, meteorites, air, whatever, it's going to get eroded down to another surface to make it, some level to make an erosional surface. And then at some point, eventually, it may become a depositional surface again. And that's what we're seeing here. Right? So we're seeing a smoking gun for an unconformity. Yeah.
Are the layers compressed on the left, or is that sort of an optical illusion? Are they actually parallel?
Are you talking about the horizontal layers or the tilted ones?
Below that, the tilted.
Ah, yes. Great spotting. When they are actually parallel and you don't have a perspective issue, then they look equally, aligned. Here it's maybe a combination of the two, because I think you've got some relief coming up. This area is closer to you than that or that. Good spotting. So clearly Mars had lots of ancient tectonics, but no place do we see any indication of a subduction zone, or any indication of spreading centers where new crust came out. So no global plate tectonics. But in the past, there was extreme version of loss of heat in a hotspot way in Tharsis. Now, though, it's conduction through basically a single crust. That means that in the past, Mars was way down here. No plate recycling, so 0% of anything puts you on the opposite line, right? But some conduction, but overwhelmingly hotspot volcanism. That's where Mars was on this diagram. Now Mars has gone up to join the Moon and Mercury. What about our evil twin sister? You can't see the surface visually, but you can image it by radar. And some people have done this an amazing job. I'm going to focus in for a moment here on an area called Giniki Kazma. And this guy, you know, in fact, the same guy who trained Dave Scott to do geology on the moon, mapped this area and showed this to be an elevated area where there's volcanism and some forms of rifting. And a European spacecraft mapped the planet with microwave thermal emission, and lo and behold, found a hotspot. Now, you automatically underestimate the temperature difference because you're looking through 100 atmospheres, Earth atmospheres of atmosphere. So it's all diffused. But they saw an absolute, no doubt about it, in the area where Jim Head and his colleague had mapped what looked like volcanic features. They found a hotspot. And then, 2 days later, they passed over it again. That spot had expanded, and some of the hot stuff had moved down slope. Talk about a smoking gun. This is a volcanic smoking gun. You caught Venus in the act of volcanism. Then, what to me is my favorite part of Venus. I should explain what this is. This is a kind of radar image, but it's made by the Magellan spacecraft. These black areas are data dropouts. So it goes along in an orbit that was sort of almost north-south. And it's looking off to the side and collecting this data on roughness of the surface. And there's a whole, you can see the size of each of the orbits worth of scanning. And a whole bunch of places that were just data dropouts. Okay, so you ignore the black stuff. Now I want you to tilt your heads way to the left and look here and look there. And add yourself to the ongoing debate. Is that a rat or a puppy dog? I find that there's a correlation. The answer to that is highly correlated to whether someone grew up in urban or rural areas. I'm a rat guy. But you look at it geologically, and you can map out faults. Each of these is some kind of fault. And I've indicated here things that are normal faults that involve extinction. Now there's some out here, you wonder what those are. Those are related to flexure because of weight added here for all that reason. When you press down on a ball or something, you're adding some stresses to the area around where you deform the surface. And some of that is tension stress. But the main thing here is we have extension by normal faulting up in that area. And down here, you got thrust faulting. So it's extending there, shortening there, and lo and behold, you got some funky oriented faults there that play the role of strike slip. So what happens if you're extending here, shortening there, and slipping sideways there? You have a region that has moved southwestward, and that's 1,000,000 square kilometers. You saw this on Earth, you immediately said, "Oh, I've discovered a plate." But then you'd say, "And where's the spreading center with new magma coming up to make new crust?" It didn't go that far. It didn't do that. Where's the material that's moving down into the mantle? No, some of it went down, but it just kept on going down at different points. You didn't have a whole plate going down. So no, this is a plate wannabe, but it's not a plate. So need to step back for a second and ask, what makes it possible for there to be plates on the Earth? Remember, I talked about this thing, the lithosphere, the outer stuff that acts the way you think a rock should. It's rigid. Below the crust is the mantle, and it's pretty close to chemically homogeneous. But it's not homogeneous in viscosity. You always have a battle between temperature, which makes it want to be inviscid and weak, and pressure, which actually has the opposite effect. And there's a third component that you might not suspect. It's water. I'm not talking about pools of water or anything like that. I'm talking about water molecules in there with the mineral structure. And it turns out you could have 1/10 of 1% of it being water, and it makes orders of magnitude difference in the viscosity. So
Higher or lower?
makes it weaker. Very good point. So if you have the mantle down here that, because maybe a little less water, but also higher pressure, is, despite high temperature, is strong, and a strong lithosphere, but in between there, you have a weak lithosphere, you've got an Oreo. Always good to eat the experiment. And that's what makes plate tectonics possible on Earth. For Venus, my first assumption would be Venus is hotter. Therefore, its asthenosphere would be weaker. But Venus also always lived closer to the sun. It's very volatile, depleted compared to the Earth. It has very little water. So it doesn't get to cheat. On the way here, I stopped to pick up some Oreos. I was hoping that this month there would be chocolate chip cookies or something back there, where there'd be a solid cookie that I couldn't shear. But imagine there is. Imagine I've got something as thick as an Oreo, but no cream in the middle. That's one way of thinking about why Venus doesn't have plate tectonics. So, despite the high temperature, that asthenosphere isn't as weak as you might expect. So Venus lost most of its water. Less water, no weak asthenosphere. No large-scale lighting plates. And despite lots of active volcanism and tectonics, no ongoing plate tectonics. That's the story now. How do you know the age of the planetary surface? What's the quickest thing? You look at an image of a planet's surface, and you know, craters, right? Counting craters. You can count big craters, but the statistics are really lousy on that because there aren't that many. If you want to count small craters, say 20 kilometers or down. Venus doesn't have any. Because anything small enough to have made a 10-kilometer crater wouldn't have made it to the surface to begin with because of its atmosphere. It would have done a Tunguska instead and broken up in the atmosphere. So you have really bad constraints on the age of the Venusian surface. So yes, right now, Venus is here. It doesn't plate recycle. We've got hotspot volcanism and conduction. It's over there. But some people have made what I find credible arguments in literature that there's something funky about what craters are on the surface of Venus, and a suggestion that the planet as a whole surface is only about 500 million years old. Just the other day. Remember, I'm a geologist. So the suggestion is that Venus can only go so long with all that heat being trapped without something catastrophic happening, meaning catastrophic overturn. Think plate tectonics on steroids. Okay, so Venus may have spent some time down there in this diagram, but it's definitely up here now. So fundamentally, planets are like birds. Okay, you put them in the oven 4.6 billion years ago, get them up to temperature, and then you pull them out. Okay. A little Cornish game hen is going to cool off a lot faster than a large turkey. Okay. In the absence of worrying about endogenic inputs of energy or radioactive decay, that kind of tells you the story about the difference between the Earth and Mars or other planets. And Venus is going to wind up in the same category. Very active, was active, and dead. But that just leaves us with these bodies that we know and what we know well in our solar system. By that reasoning, shouldn't all these little guys be dead as a doornail and have been for a long time, right? If planets really are just like birds out of the oven, then these guys should be dead and should have been dead a long time. So our type example is the Galilean satellite. You start out at Callisto, and it's a little hard to see the craters because it is, after all, an ice crust, and it does viscously relax over time. But this is a saturated cratering situation, meaning that for every 10 new craters you add, you've erased 10. You know, over time, it's not going to have more craters because new craters erase old ones. You do have faulting, as you can see, these rings around the Valhalla impact, but it's dead as a doornail. No endogenic anything happening. You move into Ganymede, you got this complex tectonics, but it's not super active now. There are some craters, but you definitely see evidence of normal faulting. There's been some controversy about why you don't see enough thrust faulting on these bodies. There's a complicated argument that I've published that I won't tell you now. I can talk about it later if you'd like. But Ganymede has had activity, as evidenced by the fact that one of my former collaborators actually pointed out this crater that used to be circular has had extensional faulting down the middle of it. So now it's two half circles separate. Europa is insane. First of all, you can't find craters. So it's really tiny things. Its surface is pretty much yesterday. Geologically, it's got a lot of these double features that look an awful lot like what happens on Earth when you've got ice rafts that collide. You get these double ridge features. And it's also got places like this that seem to cut those off. You see it put an arrow here, an arrow there, they should have fit together once. It was spreading in between. So through the magic of Photoshop, I colored that in blue. And in addition to highlighting features that got cut off, I'm highlighting in red boxes things that have crossed this. Well, geology tells you that of this thing here, things that cross it, things that got cut off by it, and this blue region, the oldest has to be the stuff that's cut off. The youngest is the stuff that cuts it off. Okay. So to try to fit this back together, I then did violence to Europa and cut all this bluish greenish stuff out to merge the two sides together. Okay. So this is an approximation of what it looked like before that extension. So this comes a lot closer to plate tectonics. There's extension. What you don't have is plate recycling, subduction. Then you move into Io, and Io makes the Earth look volcanically dead. I mean, it's just incredible. There's a plume staring at you with its shadow, another one on the edge. I've got this visible light image that I borrowed off the web, and then I now transitioned it into an infrared image. So you can see that those spots are indeed hot. They are active volcanoes. Now it'll transition back to visible light. So
Excuse me, do the tidal effects from Jupiter warm up as it gets closer to Jupiter?
you are. Keep that thought.
Okay.
Let's watch, in a planetarium software, here's Jupiter and its moons over a period of time, and watch Io and Europa. Io laps Europa every second Europa orbit. They're in what's called small integer commensurability, or basically the orbital periods are in a small integer ratio. This one happens to be the simplest of all, 2 to 1. If you had a planet like Jupiter with only one moon, even if its orbit was a little elliptical, there would be energy exchange because the body and the gases in Jupiter couldn't respond quickly enough to make the tides perfect with respect to the moon. There'd be dissipation of energy, and over time the orbit would be circularized. These orbits all want to be circular, but they've got pesky neighbors that, if they're in a small integer ratio orbital period, cause the orbits to become slightly elliptical, which means that there's a difference in their shape between their apogee and perigee because of tidal disruption. In the case of Io, we're talking about 100 meters of flexing every 3 days or whatever the period of Io is. If I take a paper clip and I flex it, you know what's going to happen. It's going to get more. Io and Europa are in one of those commensurabilities. Io kind of gets the worst of it for 2 reasons. One, because it was near Jupiter, lost a lot of volatiles. It doesn't have the water and ice. But also it's deeper in Jupiter's potential well. So a little bit of movement in and out is a lot of potential change. So you can see how the amount and timing of these low integer ratio orbital periods affects when and how much these things have the energy for tectonics. So that's a nice concept. And you can extend it elsewhere. The moons of Uranus, Miranda's only 1,160 kilometers. You've got rifts filled by ice coming up from a watery mantle. That's a really small body to have had relatively recent tectonics. It is not crater saturated, so this is not, ancient. You've got Ariel, one of my favorite ones, because a guy and I actually published a paper on it with a student, where you have the thing called corona, convection in a warm mantle. This thing's only 470 kilometers across. It's tiny. It's not even a Cornish game hen, right? I don't know what it is. It's something really tiny. It should be dead cold early on. So that all makes sense. What's going on with Vesta? Vesta, look at these faults on Vesta. Vesta doesn't have a neighbor to have tidal interactions with it. But Vesta does have something special, and Vesta has something special about it that meteorite collectors have known for a while, that there are classes of meteorite that come from Vesta. What happened on Vesta is a result. These fossae here, they're called, are the result of impact shock. If you look at the shape of Vesta, oh yeah, there's a big chunk taken out of it down here. crater called Rhea Silvia. And when people have done the modeling, you take a Vesta-sized object, punch it like crazy from an impact, and watch the seismic waves move back and forth. Where they get concentrated, where they're going to do the deformation like crazy, is 90 degrees away from the impact point. So really impressive faulting, but again, it's exogenic. Vesta didn't do it to itself. It was an innocent victim. Yeah. Vesta is the brightest of the asteroids, the only one you can see naked eye. I actually have, in a really dark place with younger eyes. But it was evolved enough to have deep mafic rocks and surface basalts and so on for these different well-known classes of meteorites. So that allows us to make a generalization. Big things stay warm and active. Little ones get cold soon after coming out of the primordial oven. Big impacts cause temporary tectonic activities, and tidal stresses can heat them up to allow it. But of course, to every rule, there are annoying seeming exceptions. One of them is Ceres, which, even though Vesta is the brightest, it's not by far the biggest asteroid. Ceres is big enough to have actually been chemically complex. If you had asked me a number of years ago whether Ceres would have anything interesting, anything other than craters on it, anything looking like a mountain, I would have told you absolutely no. And it would have been absolutely wrong. Because Ceres is chemically evolved enough to actually have had, of all things, brines. And they appear to have played a role where when you've had impact, like in opposite to a crater here, you actually have flow of material that's aided by these very high albedo brines. And you can actually lead to sort of some funky looking mountains. So Ceres is a weird exception. Pluto and Charon, you'd expect maybe they had a tidal game going on between them. Charon's got a very old surface, but no matter what interactions they had between them, it shouldn't produce enough energy to make even cryotectonics, which we normally mean ice related. And it doesn't, because Pluto cheats. And how does Pluto cheat? It's so damn cold that ice is a very strong rock. The flowing rock is nitrogen. I would have predicted that. It's mind-boggling. You know, I just breathed in 78% Pluto rock. You know, it's just an astonishing thought. And the last one is Enceladus. It's in a 2-to-1 resonance with Dione, and it's certainly got an active surface, even though it's only 500 kilometers across. The Webb telescope has imaged a plume of mostly water vapor coming out of it, out of areas near the South Pole, and they correspond to what's known as the tiger stripes. And again, thermal imaging in the IR shows that those tiger stripes are warm. So it's very consistent with a warm, slushy or watery mantle venting out into space on extensional features. You look at the body, you see the northern part is full of craters. So it's what I would have thought Enceladus would look like. But for some reason it chose in the southern area to let its energy out. And when people first studied this, they said, okay, that's fine. But measured in our not quite Système International unit of nuclear power plant, the energy output was about 20 power plants instead of 2. about an order of magnitude more than people originally thought. And that led to the question, why? So it has an interaction with Mimas, but Mimas totally lacks. Look at Older, the heavily cratered, extremely heavily cratered surface, no tectonics at all. So this raises the obvious question. A long time ago, in a satellite system far, far away, what could have caused Mimas to strike back against such heat? Irresistible. I have to do that. As much as I love the Darth Vader hypothesis here, the reason is a little actually more interesting. If you're going to flex a body, the way you heat it is different if the body is solid ice, if it's all frozen, or nearly all frozen, versus if it's got a shell of ice with water inside. That shell deforms better and actually heats up more. Well, Mimas is enough smaller than Enceladus. It was a smaller bird coming out of the oven that it had already cooled enough to have frozen all the way through. So the reason it didn't deform as much is that it had already frozen through, and it turns out that a frozen body doesn't heat up as much as a molten liquid one with a frozen shell. That plus the fact that Enceladus cheated and had a little fling on the side with Dione that it also interacted with. So we can explain the activity of Enceladus without invoking the Darth Vader hypothesis. So the rocky and icy bodies of the solar system, they have an awful lot to teach us about how to look back at our own planet. And my field of tectonics, which again is the study of things that go bump in the crust. But true plate tectonics is found only on one planet. Be it ever so lovely, there's no place like home. Thank you.
Dan, I have a question, dude.
Yeah.
Dan, how does plate tectonics come into play with wrinkled ridges on the Mare on the moon?
Oh, great question. And really relevant because I'm in the process of writing a section on that for a proposed book about the tectonic geology on the moon. Maybe I can walk off with this. In the kind of mountain belts that I study, you have thrust fault systems where there's a horizontal weak layer and another horizontal weak layer up here, and it could be even the surface of the body here, and you have a thrust fault in between, and you wind up, when you shorten, you bring all the rock above up over the thrust fault, and there's a very distinctive shape, steeper in the front side, a flat area behind, and a tilted area behind that. That's called false bend folding. And in fact, a close senior colleague of mine is the person who kind of introduced this concept, John Sutton. Wrinkle ridges are that. What happens is there comes a point when you have compressional stresses after you've had the basalt flows, but they cool from the top. They're weaker at the bottom. So they have a weak area they can flow over. They also have a weak area known as the surface of the moon to flow over. So you have a thrust fault that cuts up and all this material moves upward and you get exactly that shape. That's why wrinkle ridges are asymmetric. And if you see a north-south wrinkle ridge on the moon, it's gonna look different before and after full moon because you're illuminating it from the opposite side. Oh, yes, sir.
Does gravity make a big difference in all this?
Yes, so when you're gonna build up topography, mountain building, say you've got some horizontal forces, horizontal stresses. Eventually, if you're gonna have compression, you have to lift the stuff up. Well, the potential energy it takes, the potential energy you have, and in fact, the energy you have to put into it to gain that potential energy is proportional to gravity, which is why you can get away with relatively bigger scarps on like small moons than on the Earth. So you can't just say that Mount Hadley, whatever it was, 4.5 kilometers high, scale that up. That's a 17 kilometer, 56,000 foot mountain on the Earth. No, it's easier to make that on the moon. 6 times easier in terms of potential energy. It's also true that gravity involves when you have a crater, for example, you have a mass deficit. And somewhere down there, it doesn't like that mass deficit. So the material starts flowing upward, and that's called isostasy. And how that works is also a function of gravity. Yeah.
Hey, in the case of Mimas, I know that it's still contemplated that there could be a subsurface ocean. Maybe it's a slush ball, maybe it's an ice cube all the way through. And I know there has been some ping pong going back and forth on these ideas since the research that you presented up there. Do you feel like your thoughts here exclude those other thoughts?
No, that's a really good question. One of the issues here is that I used this talk as an excuse to go back and look at some of the recent literature. It's a more complicated picture than I presented. That's not the only orbital resonance that Enceladus has gone through. And what is clear though is that, to me, is that whatever the answer is, Mimas has had a history of a higher fraction of it being frozen than Enceladus does. And that still carries through that argument about flexing something that has a thick shell versus a thin shell. But yes, there's I saw a couple of papers that were, debating points.
Oh, they fight.
What's that?
I said, oh, they fight.
Yeah, they do. Definitely. Yeah.
First of all, thank you so much for that wonderful crash course on tectonics. Yeah, it's very informative.
Crash means something will place. Although when we crash, we do it in a very slow. But yes.
My question is, if you are given a chance to go to the moon and explore its surface, which part of the moon would you like to go to and why?
Oh my, yes. That is a wonderful question. I have a childhood love of the Hadley Rill area, and I would just love to hike down it. And scientifically, though, I think I really would like to look at some wrinkle ridges, because I really am a proponent of the fault bend fold model of that. And in my career, I was a tectonic modeler of contractional mountain belts. And I would love to be able to haul along another toy that I play with, it was a ground penetrating radar, and confirm the structure being a fault bend fold, not only for its scientific value, but because it would validate a friend and a mentor, John Suppy. So I'd probably go for that, but damn, I would want to also hop over to Tsiolkovsky crater on the other side and see what little some of the little basalt there is on the far side, and then the central peak, and I could go on, but I think there's, I should just, as an aside, this wonderful guy, Jim Head, who trained the Apollo astronauts. Imagine your first job out of grad school is, gee, would you mind coming, we've been training astronauts to do geology on the moon? His first job. He was telling me that when they were training the Apollo 15 astronauts, they were naming features, and there was this one bright, small crater on the opposite side of the rill that if you went a little bit wrong, you could actually, this place where you might go obliquely across and get to it, sort of on the other side, and be too far to get back. And he showed me this, well, the names of the other craters made sense. This one was OS, O-S. And I said, oh, I get it. It looks like bone. So it's French word. And he said, no. It means what you would say if you found you were there. Yeah.
Would there be basalt columns anywhere?
Okay, so to let people know what meant by that, basalt flows are other related mafic flows. When they cool, they're not big enough to fill their space. So what happens is they form cracks. And the physics of cracking is that those cracks like to be at around 60-degree angles. How many people here have ever driven, it's going to sound like a non sequitur, across the George Washington Bridge from Manhattan to New Jersey? You see the Palisades? And they're called Palisades because that's, you know, where all these logs in front of a old West fort were called Palisades. But they look like that because that's columnar jointing. The answer is, it hasn't been observed, but I can't imagine that it doesn't exist because you have lots of basalt flows that cooled and therefore couldn't fill their space, and the physics would be the same. But to my knowledge, they haven't been documented because they're really small scale, really hard to identify, particularly after they've been covered by regolith. Because when you look at the moon and you think you're seeing the surface, the geological surface, what you're really seeing is some few meters above the surface where you have all the stuff that's been pounded around and blown, ejected from nearby craters and sometimes distal craters. So you can't really see much of the actual basalt surface. When you see the dark morae, they look dark not because you're looking at the pristine basalt flow, but because most of the stuff that got blasted from nearby craters was basaltic. So you're looking at mostly basaltic regolith on top of basalt. So the short answer is, I'm sure it's there, but you can't see it. And okay, this makes me want to modify. Another place is I want to go there with a bulldozer to go below the regolith and look for that.
What about radar? Would that help?
Yeah, yes, and you're preaching to the choir because another area of my research was if you're in Stony Brook, Long Island, you don't have any bedrock on Long Island. Right. So you want to get students out to do field work. I did a lot of stuff with students with ground penetrating radar. And they're starting to do ground penetrating GPR studies on the moon. That would be a good way to do it. The problem is GPR wouldn't detect it well because by definition, the fractures would be vertical and you'd be looking at them from above. So it would be very hard to image. And I'd much rather go with digging equipment and port around it. So. Sorry. Oh, was there? Speak up. Whoever I can't say. Oh yeah, there you are. Yep.
I heard recently that the recent hypothesis for Cirrus is that it's did not form there in situ. It's came from like somewhere close to Jupiter, so that's why it's chemistry is very complex, is that what?
I am not up to date on that. It sounds, something has to be amiss with it. This is one where I would, if I were here with my friend Guy from Somali, I'd defer to him. I'm the geophysicist, he's the geochemist. But something is interesting there that's outside of my area. I really don't know. Okay. Yeah.
So I think we are coming to the close of the meeting. So we have, just a reminder, the picnic is on the September 20th, right?
Please volunteer.
3 p.m. at our clubhouse. Then what? The next board meeting, September 24th, 8 p.m. Well, we are at the close of the meeting right now. So thank you all for coming and